This is section 4.7, logarithmic scales. When a physical quantity varies over a very large range, those numbers can be hard to work with, really big, really small. How do we think about those together? Well, we might use what's called a logarithmic scale, where numbers are represented by their common logarithms instead. For example, if you have data that ranges from 1 to 1 billion, since the common log of 1 is 0 and the common log of a billion is 9, then on a logarithmic scale your data would only range from 1 to 9, so it's a little bit more easy to handle. We're going to look at three commonly used logarithmic scales: pH, the Richter scale, and the decibel scale. There are plenty of other quantities measured on logarithmic scales, like light intensity, information capacity, radiation. You've got an example in your paper homework of another logarithmic scale. So we're just going to grab a few of these examples. Let's start with the pH scale. Chemists measure the acidity of a solution using pH, and that is a logarithmic scale. H plus is that concentration of hydrogen ions measured in moles per liter. Using this, you can avoid small numbers and negative exponents. Let me show you what I mean. For instance, if that hydrogen ion concentration is 10 to the negative fourth, then the pH is actually the negative common log of 10 to the negative fourth. So it's negative 4, or just a nice positive 4. If you've taken chemistry classes before, you might be familiar with this scale a bit. A pH of 7 is neutral, a pH less than 7 is acidic, and greater than 7 is basic. Note that when the pH is 5, that hydrogen ion concentration is 10 to the negative fifth. So in general, if we compare that with the example above with a pH of 4, we can see if the pH increases by 1 unit, the hydrogen ion concentration actually decreases by a factor of 10. So in going from 4 to 5 as a pH, we go from 10 to the negative fourth to 10 to the negative fifth, decreasing by a factor of 10. All right, I brought that formula forward. Let's use it with an example. The hydrogen ion concentration of a sample of human blood was measured to be 3.16 times 10 to the negative eighth moles per liter. Let's find the pH and then classify it as acidic or basic. So by our formula, the pH is negative log of 3.16 times 10 to the negative eighth. If I plug that into my calculator, this is about 7.5 for a pH. And if you remember, a pH greater than 7 is basic. The most acidic rainfall ever measured occurred in Scotland in 1974. Its pH was 2.4. Let's find the hydrogen ion concentration. So this time I know the pH value is 2.4. We want to solve for that hydrogen ion concentration. This is a logarithmic equation. I think I'll take this negative to the other side first to isolate my logarithmic expression. And then I can raise both sides with a base of 10 to undo that logarithm. 10 to the negative 2.4 is equal to our hydrogen ion concentration. And that's going to be about 0.00398 moles per liter. Here's another example of a logarithmic scale, the Richter scale, which you may be familiar with as measuring the magnitude of an earthquake. In 1935, Charles Richter defined the magnitude m of an earthquake to be the logarithm of the ratio between the intensity of the earthquake, and you can see more information there about how that's measured, and the intensity of a standard earthquake. So we're looking at that ratio I over S. The magnitude of a standard earthquake, then, if it's S, the logarithm of S over S is the logarithm of 1 or 0. So again, here was our formula I over S. If we're looking at an earthquake with intensity of a standard earthquake, that's kind of where we start our scale, at 0, our standard earthquake. An earthquake of magnitude 6 is actually 10 times stronger than an earthquake of magnitude 5. Not totally surprising, knowing that we're looking at this base 10 logarithm. Here's how I can prove that. If I1 is the intensity of magnitude 5 earthquake and I2 the intensity of the magnitude 6 earthquake, well, if I call them I1 and I2, I can set up this equation for a magnitude 5 and a magnitude 6. Taking logarithms on both of those, that means 10 to the 5th is I1 over S, 10 to the 6th is that ratio I2 over S, so I just took 10 to the power of each side. So if I compare the two intensities I1 and I2, well, I1 is 10 to the 5th S, I2 is 10 to the 6th times S, so I multiplied that S over. 10 to the 6th times S is 10 times 10 to the 5S, and this was the intensity of the original earthquake. So I can see here the intensity of a magnitude 6 earthquake is 10 times the intensity of a magnitude 5 earthquake. The 1906 earthquake in San Francisco had an estimated magnitude of 8.3 on the Richter scale. In the same year, a powerful earthquake occurred on the Colombia-Ecuador border that was 4 times as intense. What was the magnitude of the Colombia-Ecuador earthquake on the Richter scale? The magnitude of the San Francisco earthquake we know is 8.3. Let's write an equation for that. 8.3 should equal the logarithm of the intensity of that San Francisco earthquake over that standard intensity. So I'm letting I be the intensity of the San Francisco quake. If we want to think about the magnitude of the Colombia-Ecuador earthquake, well, let me just call it M. I know that magnitude is the logarithm of, well, the intensity would be 4 times as intense, so it might look like this. Note that this is actually, well, the logarithm of 4 plus the logarithm of I over S. If I write it this way, it's really slick to just replace the logarithm of I over S with 8.3. So in order to find the magnitude we're looking for, we just need to evaluate this. Logarithm of 4 plus 8.3 is about 8.9. Let's look at a couple of examples of the decibel scale. Our ear is sensitive to an extremely wide range of sound intensities. Because of that wide range, this seems like a good candidate for a logarithmic scale. Again, they have a reference intensity because we're going to use a ratio, and that's 10 to the negative 12 watts per square meter at a frequency of 1,000 hertz. This is a sound that's just barely audible, or the threshold of hearing. Loudness then varies with the logarithm of the intensity. So the decibel level B is 10 times the logarithm of I over I naught. So same idea, kind of that ratio of intensities. So the decibel level of barely audible, our reference sound, is 0 decibels. So again, just like with our earthquake, using that standard intensity to start us at 0. Let's find the decibel level of a jet engine at takeoff if the intensity was measured at 100 watts per square meter. Our formula was 10 times the logarithm of I over I naught, where I naught is 10 to the negative 12 watts per square meter. We're measured at 100 watts per square meter for I, my new intensity. So let's take 10 times the logarithm of 100 over 10 to the negative 12. Plugging this into my calculator, which shouldn't be too bad because this is a power of 10 ultimately, 10 squared over 10 to the negative 12. This is just 140. 140 decibels. One more, let's find the intensity level of a motorcycle engine at full throttle if the decibel level was measured at 90 decibels. So the decibel level this time is 90. This is 10 times the logarithm of I over I naught, which was 10 to the negative 12. Let's solve this for I. So I'm going to divide by 10 on both sides to isolate my logarithm. I'll take 10 to the power of each side to undo my logarithm. And multiply by 10 to the negative 12th on both sides to get I. This is 10 to the negative 12 plus 9 is negative 3, or 1 over 1,000 watts per meter squared. I have a few problems available for you to try, one with our Richter scale, one with our pH scale, and one with our decibel scale. You can post these in the discussion for homework 10.